towards resource-aware distributed machine learning. As I was promising yesterday, I hope that we today actually get to do some distributed machine learning after all the setup and how to configure things and all that. So a quick recap what happened in the first 3 days. So day one was basically to instill on you that resource management is upon us. Clouds will have resource managers. Things will cost different money over time. We need to somehow relate that to machine learning applications. And I think machine learning is uniquely positioned to react to this kind of environment. Second day was basically just compiling and running stuff. Day three was we ran Reef on HD Insight, at least the people who had a Windows laptop in the audience. Everyone else saw a lovely error message, and thanks for reporting the error. I fixed it last night. So today, I want to go back to this running Reef on HD Insight for the people on Macs and Linux. So yesterday night, one or two of you reported the issue. It's a very subtle bug, and it's due to the fact that we kind of got done with all of this for the summer school just in time for the summer school. So we didn't test on anything but Windows. But now it's fixed. So please update your Reef installation. So inside of the Reef folder, execute git pull, which will download the newest source code, and then go ahead and compile it again. After that, you should be able to run Hello HD Insight on the actual cluster. I have the command line to do that on the next slide. But before we do that, please everyone do a git pull inside of the Reef folder. That will give you the newest version of the source code. And then you need to compile it such that you have the newest binaries. Okay. People fanatically typing either Facebook messages or what I have on the screen, right? So who's done with this? Okay, I'll give it a minute or two more. Yes.
Is it necessary to do the maybe clean?
Yes.
Necessary.
You don't have to do the clean. You can just do mvn install.
Okay.
I'm just paranoid about this. So this is basically instructing it to delete the compilation outcome of the last version and recompile everything. It's the surefire way to make sure that you get the actual newest bits compiled. So while we wait for everyone to catch up, the bug was actually subtle, for those of you who are interested in why it didn't work. The bug was that on Unix systems, if you have a path, let's say the class path that Java uses to load the classes, the entries in that path are separated by colons. If you have a Windows system, they are separated by semicolons. We do the prudent thing of asking the system for what is the correct one on this machine and use that. Guess what? When you are on a Mac or on a Linux system, the answer will be colon. And then we send that string to a machine that runs Windows. And that doesn't understand this, and we get the weird error message. So that was the actual error. It was a one-character change in the code base. Okay, who is still trying to do this? Okay, 1, 2. Is Sergey in the audience who can maybe help? Apparently not. Okay. So is it running or is it... okay, good. Then we can move on to the next slide, which is straight the copy of the slide from yesterday, which is you need to set this environment variable, which you either do in PowerShell with this env::reef HDI_conf equals this file name, so you put the actual path there. I saw a few people who took me too literally yesterday and put path/to somewhere in there. Do not do that. It shall only be the actual path to the file, right? If it's in your home folder, this would be ~/mlss.json. And if you renamed the file, you also want to have it point to the actual file name. And after that, you can run it, and you should get some output. And this might take a while, so I'm going to leave that up for a little while as well. And I'm doing this again today because all of the machine learning examples will only run on HD Insight, because we run on a data set that's a couple of 100 gigabytes in size, and you don't want to download that to your laptop, I suppose. I mean, those of you with terabyte SSDs in their laptops could, but most can't. Okay, who has tried this and it worked on a Linux or Mac? Wonderful. We at least have 1 or 2 confirmations that I actually fixed the bug. That's good news. Yes?
I already run the job, and I accept the job. It already says finish, unlike yesterday.
And it ran through?
Oh?
So when you do the status thing, it says...
Yeah, it says finish.
Oh, great. So it worked for you. Oh, this is all very bright here. This is the only spot I can stand where I'm not blinded, so... Okay, who has tried and it worked? A few. Who has tried and it didn't work or didn't work yet? Anyone getting any error messages when trying to do it? In which case, this path is probably, you need to put the path to this file. Okay. Sergey, can you help her? She gets a class not found. Okay. Yeah, this is a general Java bug. This has nothing to do with whether or not the refix I put in yesterday helps you. Okay, and you have these commands also on the slides from yesterday, which I uploaded to reef-project.org. So you don't need to frenetically kind of type these or copy them or whatever. They are on the slides from yesterday. Okay, just as a reminder also from yesterday, if you want to check on the status of your application, we have a little command line tool where you provide this dash status and then the application ID, and it will print out something like this, right? There will be a JSON document, which is this with these curly braces, will be printed out, and it will have a state and a final status. So state is what it's in right now. And final status is what was deemed to be the final outcome of your execution. So this could be running and accepted or something like that, while it's still running. Who has seen the successful execution? I'm just trying to figure out that I'm not losing people, right? Because the other way around, me assuming that you will ask questions when you get stuck, is not as secure as me asking who is still with me. Okay.
Undefined status? Undefined status?
You are in an undefined status. That's awesome. Maybe it's still running. What is the final state? Is final state undefined and current state running? Because final status will only assume a value of succeeded or failed, right? And while it's still running, it will say undefined.
Is there a current status? Yeah, state line.
So it's running, okay.
Sorry.
Yes?
Should the JSON file be on the path or?
It doesn't have to be on the path. Only this ref_HDI_conf environment variable needs to point to it. Any other open questions on how to submit and check whether it ran. Again, all of this information is on the slides of yesterday, and you can continue doing that while I'm going through some more of the background of what we're going to do today. And hopefully by the time we run the machine learning code of today, all of these kinks have been resolved on your machines. Was there a question or was there success? There was success. Awesome. Okay, last command was this accessing the log. And there it's ultra convenient to give it, oops, wrong button, to give it two parameters. The first one is the application ID. That's the one that was printed out when you submitted the job. And the second one is a folder into which it will store all the logs, one file per evaluator that you had. If you don't give the second parameter, it will just print out everything to your console window. Right? And you can redirect it to a single file if you want that. Okay, so while some of you are still doing this, I'm going to continue talking about things actually towards distributed machine learning. So let's do that. Today we won't do resource-aware machine learning. We will do distributed machine learning on Reef. One core primitive that we need for this is group communications or collective communications, as they are called. For those of you who have ever interacted with MPI, that's the feature of MPI, that you have operations that involve more than one machine and produce one outcome. So, so you have communications with many participants, many machines, and they collaborate on one collective communication task. And we're going to look at two of those for the sake of this tutorial. Yeah, I might have to go to the laptop to push. The first one is broadcast. Broadcast is super straightforward. You have a single sender that sends the exact same value to all the receivers. Right? This could, for example, come up when you want to distribute your model. If you do gradient descent or any of these algorithms, you might want to distribute your model to a couple of machines. Each of those machines holds a partition of the data set. Right? So broadcast is the way to go if you want to send the same value to a couple of machines. So now the question arises, why would you use broadcast and not just a loop over sending to each of them individually? That's because when people implement these collective communications libraries, they put any number of optimizations into this operation. So, for example, you could have a tree to distribute the data. If the data is really big, you could send to two machines, which themselves send to two more machines, and so on, to distribute the data. When you do that, you might want to take into account where those machines are. If you are in a traditional data center setup, where you have a couple of machines per rack, and in between those machines you have faster internet, network connections than in between racks, then you want to take that into account. You might even want to do some form of a peer-to-peer send, so such that you basically do something like BitTorrent, where someone puts the file up and everyone else gets to download it. You can do this also in the data center. So all these optimizations are totally feasible behind the very same operation. Send this data to a couple of recipients. The second operation that we will need for today is reduce. This is in many ways the exact opposite. You have a couple of senders and one receiver. The senders send each their own value, which then gets aggregated, and the aggregated outcome becomes available to the receiver. So again, in the case of a simple gradient descent, the gradients would be computed on all of the machines. They just got broadcasted the model. Then they go ahead and compute a gradient on that data set and send the gradient up into the reduce operator. And then the master node would get all the gradients, update the model, and continue. So again, why would you do that and not just orchestrate it yourself? Well, there are a couple of optimizations that you can do, again. If you think about, our models are typically in the order of hundreds of megabytes, right? If you learn a linear model over text, you have one dimension per word in the English language. and you end up with very high dimensional vectors that you have to transfer over the network. It's very likely that when you send all of them from, let's say, 100 computers to one, that the network interface of the one that needs to receive will become the bottleneck of this operation. So you just sit there with 100 machines waiting for the network interface of the one machine that needs to receive. Again, there are common tricks that you can play. So you can have an aggregation tree where any pair of two machines compute their sum and then send the sum to yet another layer in the tree. Or you can do pipelining, where you do the same kind of operation, but on a per dimension basis of your vector, such that no one in the whole tree has to ever instantiate more than one vector at a time. So all of these optimizations can again be completely hidden behind one and the same operator that you use. Okay, so far this has been fairly generic on what is broadcast, what is reduce, why would you use it? Now the question might have come up in your mind is, why wouldn't I use MPI if I already have used it before? Or why wouldn't I use any other communications library? So in Reef, we take a special emphasis on elasticity. If you run MPI jobs on an actual MPI cluster and one of the processes disappears, your job hangs or crashes. If you run there and you get free additional resources while your machine is while your job is running, you cannot add them to the computation. So this clearly doesn't fly in the cloud when the price of resources and the availability of resources changes with some frequency. So you cannot just go ahead and say, well, in that case, I'll just restart my application that ran for an hour already, right? So it's very important that this is the main difference of the group communication library in Reef over, let's say, MPI. And it's only fair to say that the other main difference is performance, because MPI has been optimized for 30 years and our group communications library for 3 months. So you will see some performance differences there. So in elasticity, I like to distinguish between voluntary and involuntary elasticity. Voluntary elasticity gives you a chance in your algorithm to react to it or to initiate it. Let's say the resource manager comes back and says, hey, you can scale your computation up now, right? Then you have a choice whether or not you want to do that. This comes back to this question of relating cost to the machine learning outcome. The other kind of elasticity, which is far harder to deal with, is involuntary elasticity. In the voluntary case, you can always just ignore this fact and say, hey, I'll continue running on the machines that I have. Not doing anything is a fine decision. In the involuntary case, there are 3 cases to consider. The first one is the obvious one, and that's failure. Any node in the cluster can fail at any time with some probability. So if you have thousands of them in your computation, one of them will fail, right, if you run for a day or so. There's no way to avoid this situation, so you have to deal with it one way or the other. For smaller computations that run in the order of minutes, you often don't hit an actual failure. For large computation, you often hit them. The other cases where involuntary elasticity comes up is soft and hard preemption. So preemption might happen when you are running on a cluster, you are entitled to, let's say, 100 containers on that cluster, but the cluster management system sees when you submit it, the cluster is empty, so it gives you 500. And you say, okay, I'm going to run on 500 containers. This is a very common case on production clusters, that they are empty at some times. So you go on and you run your job with 500 containers. 5 minutes later, that very important production job comes along that needs to run in the next hour or so to produce the next advertisement model or something. And it is entitled to 400 out of your 500 containers. In which case, the resource manager has essentially 3 options. Delay the other job till you are done. That doesn't fly because the other guy probably paid for the cluster. If you're a researcher and they are the advertisement team, this doesn't fly. The other option is to go ahead and kill your job, right? And say, we will reschedule this whole job at a later time when we have the resources available again. That's unfortunate, especially if your job ran already for a little while. The last case, and that's the preferable one, is part of your computation gets terminated, but other parts can continue. Now this is tricky because you have to figure out how to make that happen. And there are two ways in which the resource manager might tell you about this. The first case is soft preemption, where you get a message from the resource manager telling you, hey, please vacate those 5 containers, or please vacate a total of 100 containers of a certain kind. And then you have choices, right? You can decide to give up on the data that your active learning method tells you is not that interesting in the first place. You can reshuffle data if you want to do that. You have choices. The other case is hard preemption. That is, if you either fail to react to the soft preemption attempt, or if the cluster is just configured to do only hard preemption, then it will just take containers away from you. That will not look any different in effect than failure. Because whether or not a machine fails or your process on that machine is killed is somewhat immaterial for what happens to that process, right? Because it's just gone. And now you have to deal with the failure scenario. The one difference is that you get some indication that this wasn't actually a failure but a preemption event, so you don't have a chance of just asking for yet another container to run this part of the computation on. So the reaction might be different in your algorithm or in your system to preemption than to failure, but the effect immediately is the same. Okay. So I'm going to focus in the remainder of this lecture on involuntary elasticity, because the voluntary one is kind of straightforward, at least in what you need to do. They're very interesting questions in what you could do. So let's talk about involuntary elasticity. In Reef, we take the approach that we handle all these events quietly, in the sense that if a machine disappears while you compute, the operator that's currently running will just happily continue. When you execute another broadcast or reduce, it will just run on all machines that are still available. Right? So when you write your code, you can just happily use broadcast and reduce, and if machines disappear, it will continue to work. That's the first principle that we do in our group communications library. Now, in the broadcast case, this is super obvious, right? Assume that it's not the sender that fails. If one of the receivers disappears, well, we just don't send it to them. In the reducer case, it's a bit more involved. Assume that one of the senders in the reduce case fails, then we make it so that it appears as if that reducer never was part of the computation, never was part of this reduce call. Okay, so now let's imagine we run our job and it's kind of a loop around broadcast and reduce, and we have machine failures one after the other, right? Let's say we start with 100 containers and machines disappear. This will make it that we still run, right? But we will run on less and less data because every time a machine disappears, we quietly move on with life. That is not the desired behavior in many applications. In many applications, you actually want to run on all the data. Turns out that in machine learning, it often is a totally acceptable way to deal with failures, just to quietly ignore them and move on with life. But when you want to react to it, we give you an API by which you can query for topology changes. So you can ask the group communications library, hey, what changed in the set of machines I have since I last asked? That way, you can, for example, structure your algorithm in a way where if it is a loop around broadcast and reduce, you ask before entering any of the iterations, did anything change in the topology? Were machines gone missing? Were machines added? Right? Were machines preempted and all that? That allows you to react to these topology changes. Yes?
Do we have to keep track of what was the previous topology, or keep track of the queries between them?
So what you get is the changes since the last time you asked. So you basically get a set of added and removed nodes, and then you can make choices based on this. Right? So this is, in the example that we're going to use, I think tomorrow when we talk about how to deal with failure in machine learning, we do this literally at the end of each iteration. We check whether anything changed in this iteration. And then we have choices, right? We can say we discard what we did in this iteration because we suffered a failure, or we can have some remedy, such as if we lost half of our cluster in this iteration, maybe we should use a slightly lower learning rate for this step, ask for machines to come back, and then continue. Right? There are many choices that are possible, many of which are open questions. And I mean, you all need a PhD topic at some point. I would love for some of you to help us out on that. Speaking of machine learning, let's do some of that. And I promised at the very beginning of this lecture that we will do very, very pedestrian machine learning and fairly advanced system stuff. I think given all the struggles we had so far, there's no question on the second claim. We haven't done anything in terms of pedestrian machine learning. So let's do the most pedestrian machine learning that you can think of. Let's do linear learning. So we have a data set of examples, and the data set has labels and features. Has labels and features. The feature vectors are called X, as in every machine learning paper on the planet. The labels are called Y. And we are looking for a predictor such that f of x is close to y. This is kind of the canonical case of what you do in machine learning if you have to explain it to your friends, right? Okay, so in this case, because we do linear learning, we say we are looking for some weight vector, w, such that this expression is minimized. We compute the loss over all of the examples, and we want to minimize that loss and the regularizer. And for sake of simplicity, I do L2 loss here, and I do L2 regularization. But of course, any other formulation in this SVM style of optimization functions is conceivable. In fact, in the code, we will do logistic regression. So now that we have the most simple, or one of the simplest learning tasks that we can think of, let's think about the most simple algorithm to optimize this thing. The simplest parallelizable algorithm. The simplest parallelizable algorithm we came up with for this is we do batch gradient descent. So in each iteration, so we start with a random model, and each iteration computes a gradient over all the data points, because that's the only thing that's data dependent. And then we compute an update over for the model, which is do a step in the direction of the gradient and shrink the model a little according to the L2 regularizer. So I was talking about broadcast and reduce earlier, and I already alluded to how would you implement this sort of algorithm with broadcast and reduce. So the first step, all of these computations can happen on partitions of X, right? Because this is just a sum over all the things in X. So you split X onto multiple machines, and then you can compute the partial sum on each of the machines, and then do a reduce operation to get the total sum of the gradient. So far, so easy. Then on this master node, which receives all of this information, we go ahead and compute a new model, which we broadcast to all the machines holding the data. Right? So we get away with using only 2 operators. As a matter of fact, for those of you more familiar with MPI, we would get away with just an all-reduce operation, which is just stringing broadcast and reduce together, logically. In the implementation, this offers some optimization possibilities. So how does this very simple learning algorithm look like when we implement it on Reef? In pictures. We will do code right thereafter. Come on. Okay. So the driver goes ahead and requests some evaluators, some number such that we can load all of the data into main memory. And in this case, of course, because it slides, Yarn is nice to us and gives us exactly the right number. Then the driver goes ahead and sends a task to each of those evaluators that loads the data from disk, parses it, and stores it in main memory. After that, these evaluators, and you recall that this is actually happening in a context, hold on to the training data, to partitions of the training data. So now that we have this set up, we can go ahead and allocate an additional node, which will serve as the master in this, and then send compute gradient tasks to the machines, and update task to this master node, and the computation will go through in loops around this broadcast and reduce operators. So far, so clear? Because it will be decidedly less clear as soon as we look at code. So one question that one might ask here is, why not use the driver for the purpose of being this master node? And on HDN side, that would be a perfectly fine choice. And I'm going to explain why. These containers, even though I present them here as a uniform grid on some cloud, there are distances between them in terms of the network topology. So if two machines are on the same rack, you might have 10 gigabit Ethernet between them, or even InfiniBand or some of the more sophisticated networking technologies. If they are in different racks across the data center, you might have to go through what's known as the top of rack switch to be connected to that other rack and then to that machine. When you initially submit your job, so what that means is you want all of these to be on the same rack or as close together as possible because your computation is somewhat network bound. You want to exchange messages fairly quickly between them. You don't want to sit there and wait for that one machine that's far away in the network. When you first submit your job to Yarn, it has no idea that this is what's going to happen. So when you submit the driver, it ends up basically on a random node, right? Or on a node where there might not be enough machines nearby to execute your whole computation. When you do this extra node or extra container to be the master, you get to choose where to put that and everyone else. That's why it's preferable to have the master as a separate node. Now, I said that this doesn't apply when you run on HDN side, and that's because they make it appear as if everything is equidistant from everything else on these HDN side clusters. There's a whole paper on this flat network topology that they built for this. And on HDN side, it doesn't matter that much. You have about the same network bandwidth between any two nodes in the cluster. But that's why in the general case, when you have your typical rack-based data center network, this is a convenient trick to get more performance out of it. Any questions so far before I switch to the IDE? Yes?
Is it possible to make executor to allocate on the same node where's the data?
Yes, good question. So in MapReduce, one of the hallmark features is that you send code to data and not data to code. What that means is you go ahead and ask your distributed file system, which runs on these very same nodes, ask where are the input files that I'm working with, and then ask for allocations on those machines. That's exactly what the Hadoop MapReduce library does. It asks first to the distributed file system, where's my data? And then it goes to Yarn and asks for containers near that data. In this case, of course, we could do that. And in the case of Azure, that might actually be a good idea. But in the general case, for these communications-intense computations, that doesn't strike me as important as being close together with each other for the networking. Because if you think about these models being roughly 100 megabytes, and then you do 100 iterations, then you have 10 gigabytes of transfer that you have to do between these nodes in the actual data path. So it might be beneficial for some of them to load the data at the beginning through the network in order to make that path efficient. So there is a trade-off here between being data local and having all the machines on the same rack to get the communication fast. So the answer to your question is yes, we can do that. The real question is, should we? And the answer to that depends a lot on where's the data actually, what is the kind of algorithm you run, what is the amount of communication you expect to do, and how often, right? If you have iteration runtimes of several minutes and at the end of it exchange 5 kilobytes of data, then being data local is probably good. If you have iteration runtimes of 3 seconds and at the end of it you exchange 100 megabytes, then you probably want to be all on the same rack, discarding this goal of data locality. Make sense? Okay, any other questions before we look at code? Okay. Unfortunately or fortunately, the code is not in the repository you already checked out, We made a specific repository with the example code that we use on the slides. You will find also the Tang example that I used yesterday in this repository. And you know this kind of slide by now. We have a special repository for the Machine Learning Summer School. It's just called mlss.git. Inside of it, you find two folders. One is BGD for batch gradient descent, and the other one is called Tang demo. That's for the code that I used in yesterday's slides about Tang. Feel free to use adapt as you see fit. All this code is Apache licensed, so if you base your own work on it, it's fine. I'm going to give you a second or two to do this. Yes?
Should we put that in the read folder or one level?
Oh, one level up. Please do not check out repositories within checkouts of other repositories. I'm pretty sure that Git is awesome enough to deal with that gracefully. But I'm not awesome enough to untangle that. And while everyone is doing that, who still has struggles with running the Hello HD Insight example? I suppose you, because you're sitting with Sergey, but anyone else? Yes. So what is the issue?
I'm not sure. I had the failed before.
You had a failed.
Yes.
Did you pull the latest Reef code and compile it before submission?
I pulled it, but I didn't compile it.
You need to compile it. mvn-d skip tests install. Anyone else still having issues with the running Hello HD Insight? Okay, whose computer is done with the compilation of this code? Okay, I'll give it another minute. Because right after this, we're going to hammer the cluster where each of you submits a batch gradient descent run to the cluster. Let's see whether that breaks it or not. I think what you really need for this kind of lecture is a group chat where I can copy this text and you can copy it out instead of typing it. There goes a startup idea. Someone needs to pick it up and make it into a product. Integrate chat into presentation software such that many people can subscribe to it. Because I just realized that the next command line you're going to type is incredibly long. So what I will do is I will show you the command line and immediately after that post it onto the Google group. Because otherwise we'll be here like 10 minutes figuring out where the typo is on the command line. Actually, I think I can do this without turning this slide away. Let's see. Yes, I can. Awesome. Let me post it on the... Is everyone subscribed to the Google group? I hope. Now I need a browser. There we go. Lovely. It copied it with formatting. How do I get rid of that? Normal. There we go. Okay. back to this. So I just posted the following command on the Google group, and now you know why I posted it. It's somewhat inconvenient. If you run it, or when you run it, you will actually submit yet another reef job to the HD Insight cluster, which performs batch gradient descent with a logistic regression loss on a data set. While you all do that, I will go over the various things in this command line and what they mean, and then we will relate them to pieces of code. So first of all, we prepared a data set that's based on the practical terascale learner paper by Alec Agarwal and Olivier Bosquet and John Langford. And it's in this folder, training data -final / and then it's split into many parts. If you use 4 digits and then a star, you will train on 10 files. Right? If you use 3 digits and then a star, then it will be 100 files, and it might take a little longer for you to get all the resources to run on the HD Insight cluster. Because for each of those files, we instantiate one container. Yes?
I think for Mac users, it's target /.
Yes, sorry. So for Mac users, it's target /. Actually, I should have changed this because on Windows it doesn't matter. So target / would have worked there as well. Okay, that's one parameter that you might want to play with. You can run on different subsets of the data or even more of it. Would be interesting whether it runs on all of it. We haven't had the time to try this before the summer school. The second parameter that you give it is this dimensionality. That's the number of dimensions that you want your model to have. And in linear learning, that's the number of dimensions that your training data has. Of course, in practice, if you have these very high dimensional models, you might want to consider using the hashing trick. Has any of the lecturers covered that, the hashing trick? I suppose Alex did, right? Okay. So in this case, to keep the code simple, we didn't do that. If you have very high dimensional problems that are sparse, like this one is, because each feature is whether or not there's a co-occurrence of 2 gene sequences in the data set. So most of them are 0. The hashing trick can help a lot. The next parameter is again more of a systemc parameter. That's the number of iterations you want to allow as a maximum number of iterations, right? And this is 10, such that it actually completes within, hopefully, this lecture or by the time you check back in after the party tonight. The next parameter is the well-known regularization constant. In this case, I don't know, it's 5 to the power of -5 or something. Shravan, one of the team members in Redmond, has tuned this such that this actually results in a good model at the end. Of course, if you actually do this on this data set for the first time, you might find yourself tuning that a lot. The next parameter is again systemc, and that is the amount of memory that this job will ask for each of the evaluators. In this case, that's 3 gigabytes. The reason for that is that on the cluster, each individual machine or virtual machine has 6 gigabytes of memory, and the minimum you have to get is 1 gigabyte and multiples thereof. So 3 gigabytes is the happy medium where we can get 2 containers per machine and we can max out the cluster. And of course, we conveniently size the files such that each of those fits into a 3 gigabyte container. I think there are 2-point-something gigabytes on disk, each of the files. Lastly, there's this -loss parameter where we pass in a weighted loss function. I was mentioning that most of the examples have a negative label. And that's very inconvenient if you just train on the examples as is. One of the ways to deal with that is to weigh the loss on one of the classes, in this case the positive class, much higher than on the negative class. You would expect to set also the weight for the negative class here, but that's conveniently hard-coded for this data set right now. There should, of course, be one more parameter for this. Okay, who has submitted the job? Awesome. Have you executed the status thing to see where it is?
Can we check the screen for the status?
Oh, it's also on the slides. If you go to reefproject.org, and then the slides of yesterday have that command line. It's running. It will be running for a while. I think each iteration takes 45 seconds. There is a minute or so load time at the beginning to load the data. So it should be running for a little while. And of course, if you run more iterations, it can take a lot longer. OK. I'm going to switch this to show you some code. And given that it's 4:52 already, I will show you kind of the entrance point and a bit of the highlights, but not at the same level as we did it for the Hello Reef case. No, we hope and pray that the screen will work nicely enough. View presentation mode. OK. Good. Let me quickly go. This is the driver code. And remember, we follow this principle that whatever you want to use in your application, you just depend on as parameters to your driver, and it will magically work, assuming that it's also in the configuration for the driver. If you look at this, we get this data loading service, and we get the group communication service, or group communications driver here. And this is just, it keeps all the parameters for us. It's not that important for right now. And then the interesting bit happens with the group communications driver. So what we do is we make what's known as a communications group. I talked about all this. We add operators, and when things fail, you can ask and all that about the changes. We do this on a per group basis. You can have multiple independent communications groups in your application. Let's say you run 2 batch gradient descents side by side because you want to know which one is better. Then you would make 2 communication groups. And the communication group is this object on which you can ask for changes and all that. It's just one layer of indirection which allows us to have multiple sets of operators in the algorithm. Now we need to configure it. And in this case, we have the 2 main operators are the broadcast and the reduce. Let me just scroll to them. There we go. Do they all fit? Kind of. Skip the first one for now. I'll explain that in a second. This guy is used to broadcast the model. And when you add an operator to the system, you have to make them known up front to the system. You specify a name, and there we play the same game as with tagging parameters. We name them using classes. That way you cannot mistype them. You cannot write a task that is supposed to be the sender, and it sends to just a name which is a string which doesn't exist or anything like that. You cannot mistype because we use class names for this. Then you have to give it the ID of the sender. That's the task identifier. Remember in the Hello Reef case, we gave the tasks a name, the identifier. This is the identifier of the task that shall be the sender in this broadcast. And of course, the data needs to go somehow through the network. And in order to go through the network, it needs to be turned from objects in memory to a byte stream that we can actually send through the network. And for that, you call setDataCodec class and specify how you want that serialization to happen. In all of the examples, we use standard Java serialization. Let me be very clear about this. It's a very bad idea actually to do this in any large-scale system because Java serialization is slow. But in order to keep the examples kind of easy to read, we rely on that because it removes any other serializer would add boilerplate code, and we have plenty of that already. The second operator that we add is this reduce operator, and we give it a name, which is again just a class. In this case, it's the loss and gradient reducer. The name says what it's going to be used for, right? It's the thing that gets a loss and a gradient and aggregates these up. In this case, again, we give it an ID. In this case, the ID of where shall the reduced content go to. It's the same, right? We use the same kind of variable to indicate this. We need to set a codec again because, well, things need to be serialized and sent through the network. And of course, the reduce doesn't just perform plus or anything like that. You can specify your reduce function that you want to use. As a matter of fact, you have to. That's the operation that gets 2 of the inputs and produces 1 output. Right? It gets executed along the lines of this aggregation tree that's being built. At the end of this, you call finalize, and you are done with setting up the group communications library, which now knows enough about your topology to actually construct the communication graphs and all that. There's a little bit of boilerplate code where you have to specify what kind of operators you want. There is one operator at the very beginning, which is called the control message broadcaster. That is used to tell the individual slave nodes what to do. Right? This will be very important tomorrow when we add line search and other operators to this algorithm, where you can broadcast, let's say, a vector, but you also have to tell the machines that receive this, is this a model and am I supposed to compute a gradient? Or is this a descent direction and a set of points at which I shall evaluate the loss function and send that back? So that's why there's this control message broadcaster. And I completely forgot to tell you in which class we are such that you can follow along. It's in this examples.nggroup.bgd.simple, simple because it's a simple-most BGD. And inside of that, it's called BGD driver, for those of you who are following along in code. Okay. So there's another kind of nicety that we use here, and that is this driver behind the scenes is configured with what we call the data loading service. That's where all the file names and stuff like that went. And the data loading service will make it so. It will do the first step of the pictures that I showed, which is allocate evaluators, go ahead and send a task there that loads the data into main memory, and then report back. So you, in this code, you only start at the point where it reports back. The data is loaded, everything's good. So these available, oh, no, we have that again. These available containers or contexts will be shown to you as active contexts. Let me just do that. There was another handler that I wanted to unfold. There we go. There we are. And do presentation mode. Okay, I only have 1 minute left, so I just want to point you to some of the entrance points. So the context active handler, the only thing that it needs to figure out is, hey, is this something that I already configured with the group communication stuff? If so, if not, then please configure it to contain all of the group communications code. Again, just because there's an evaluator doesn't make it so that it's part of this communications group. So you have to send some code there, you have to set up some configuration such that it knows its place in the communication group, where to send the reduce input and where to receive broadcast output from and all that. If it has already been configured for that, then we just submit a task to it. And unfortunately, we are out of time. Maybe I can go over this code with you tomorrow, or you just follow along kind of the calls, right? From this point on, you do a submit task, and then you can have a look. I want to quickly go back to the slides to close what we did today. So you all have done that, and if you don't see in if in an hour your job is still running, or if in an hour you see a failed, please drop an email on the mailing list such that we can look into it. Okay, so what have we done today? We have ran Hello Reef for the 3rd straight day in a row. This time everyone ran it on HD Insight, and life is good. We can do actual machine learning now on HD Insight. I have introduced the group communications library in Reef and how it is different from MPI that you might have seen before. It's especially different, not in breadth of operators. MPI has many more operators, and it's actually way faster than what we have today. But we focus on elasticity. So you can add and remove evaluators or tasks to that group communication at will. And if these adds and removes happen without your control, involuntarily, you query every once in a while what were the changes since you asked the last time. Last thing we did is I showed how to do a simple batch gradient descent, learning a simple linear model on Reef. So we use broadcast to broadcast the model, reduce for the aggregation of the gradients, and the whole computation went through in a loop. And for this, I didn't show you this in the code, I only quickly mentioned this. There are two contexts on each of the evaluators. One which provides the data set, and I mentioned that you can just trust that the data set will already be there by virtue of the service that we use for that. And the second one being used by the communications library. Good. That was it for today. Tomorrow we will actually go after the elasticity aspects of it and look at how can we react to the various elasticity events in machine learning. Thanks.